In this video, we are going to learn about the linear independence of vectors. Let's continue our journey with vector u equal to 1, 2, and now let me take another vector u dash 2, 4. I want to know that is it possible to take some linear combination of u and reach u dash? The linear combinations of u are just c times u, where c belongs to r. Clearly, if I take u twice, I would reach this point 2, 4. So yes, u dash can be written as a linear combination of u. Now can this work the other way around? Matlab, can I write u as some linear combination of u dash? Obviously, half of u dash is u. So these two vectors here are aptly called linearly dependent vectors. You'll notice that any vector that lies along this green line will be linearly dependent with the vector u or u dash. Now let's try to check if v equal to minus 3, 2 is linearly dependent with u and u dash. All the linear combinations of u will always end up on the green line, but v doesn't lie on this line. So v and u or u dash must be linearly independent. So v is linearly independent with u or u dash. Now time to jump to 3D now. Let me take a vector p, 1, 2, 0, and let's try to locate it in 3-dimensional graph. This here spans a 1-dimensional line in a 3-dimensional vector space. Let's check if this vector is independent with vector q equal to 0, 3, 0. Since q is not one of the linear combinations of p, as it does not lie on the blue line, and at the same time p is not one of the linear combinations of q, since it does not lie on the green line, we say that these vectors are linearly independent. Now because these vectors are linearly independent, each vector adds something new to the span. Pehla vector alone gave me just a line. Dusra alone gave me another line. But if I take linear combinations of both of them, I get a 2D plane given by z equal to 0. Now let's add another vector to the mix. R equal to 1, 5, 0. Or अब let's check if p, q and r are linearly independent or not. Several ways to do this, and we will learn some faster methods in later videos. But for now, let's check if r lies in the plane spanned by p and q, that is the xy plane. R ka z component is 0, so it must be in the xy plane. So these three vectors are in fact linearly dependent. At least one of them is contained in the span of the rest. And now we are ready for the formal definition. A set of vectors are linearly independent if summation ci vi is 0 only when all the c's are 0. अगर मुझे एक भी non-zero c मिल गया जिसके लिए summation ci vi equal to 0 holds, तो I say that the vectors are linearly dependent. Vectors p, q, r पे ये टेस्ट लगाते हैं and let's see if we can figure out the value of c's for which summation ci vi is 0. c1p plus c2q plus c3r को 0 करवाना है by choosing some values for c1, c2 and c3, except of course the trivial solution where all of them are 0. So I'm going to leave blanks for c1, c2 and c3. Now if you observe carefully, p and q को अगर मैं add करूँगा तो I get r. So c1 equal to c2 equal to 1 and c3 equal to minus 1 should give me the 0 vector. And since summation ci vi is 0 for something other than when all c's are 0, we conclude that the vectors are in fact linearly dependent. If you wish to check for linear independence of u and v, you want to try to find c1 and c2 such that c1u plus c2v equals 0. That is, you need to find the values of c1 and c2 from these two equations. The only solution to these equations is c1 equal to c2 equal to 0. And so these are linearly independent vectors. Now ये तीन vectors p, q and r का जो span है वो एक plane है, the xy plane in R3. लेकिन the same xy plane is spanned by just p and q. अगर p and q पहले ले लूँ मैं और बाद में r add करूँ तो r doesn't really add any new dimension to the span of these vectors. p and q के linear combinations पहले भी xy plane span कर रहे थे and r लेने के बाद भी xy plane span कर रहे हैं. So in a way r seems useless. But now let's take p and r first and check इन दोनों का span क्या होगा. These two together also span the xy plane. And now q seems useless. So for this particular example, any two vectors are more than enough for the span and the third seems useless. Another question we could ask is what is the minimum number of vectors I need in order to span a two-dimensional space or a plane. A single vector alone cannot define a plane. At max, it can give me a line or a one-dimensional space. But with two vectors, we would either have a line or most of the times, they would actually span a plane. तो ना कुछ कम पड़े और ना कुछ ज़्यादा हो, इसके लिए we define the basis of a vector space. A basis for a vector space V is a sequence of vectors having two properties at once. First, the vectors are linearly independent. That is, we don't have too many vectors. And the second, they span the space V. That is, we don't have too few vectors. So what are the bases for the xy plane in R3 in our example above? P and Q could be a basis, and so could P and R, or Q and R. What this tells me is that the basis for a vector space is not a unique set. In fact, there are infinite bases for most vector spaces. But the number of vectors in each basis is actually unique. This number of vectors in the basis is called the dimension of the vector space. In our example here, the dimension would be 2, क्योंकि कोई भी basis choose कर लो, उसमें 2 ही vectors होंगे. Now what about the basis for the vector space R5? Every basis for it would have 5 linearly independent vectors. What if I want a basis for a 3-dimensional subspace in R5? Remember that a subspace is a vector space in itself. So for a 3-dimensional subspace in R5, I would need 3 linearly independent vectors that look something like A, B, C, D, E. मतलब 5 elements in each vector, because vectors की original दुनिया is 5-dimensional. लेकिन I need only 3 such linearly independent vectors to form a basis for a 3-dimensional subspace. Let me write a set of good-looking vectors. This here is called the standard basis for R3, and they are pretty cool. But they are not the only basis for R3. Now here's a question I would like you to try. Which of the following set of vectors forms a basis of R2? And now you have 4 options. Pause the video for a minute and see if you can answer it. You don't need a pen and paper for this one. The question asks for a basis for R2, that is a 2-dimensional space. By definition, the dimension is the number of vectors in the basis. So we're looking for an option with 2 vectors. That rules out option A and option C. Option B looks fishy. 2, 2 is just twice of 1, 1. So these 2 vectors here are actually linearly dependent. So that leaves us with option D, and you can in fact check that the vectors in D are linearly independent. This question here was taken from the 2019 MSQA exam of ISI. From what we have learned in this video, we can conclude that a set of n vectors in Rm must be linearly dependent if n is greater than m. Think about why this is true. What I do when I come across such general statements where there are a lot of m&ms is that I start by assuming some numbers for the variables. And once I can figure it out for say n equal to 3 and m equal to 2, then I try to generalize it. That's it for this video. Just a little heads up, you might not be able to solve some questions related to this topic just yet. But don't worry too much about it. I'll cover them in later videos when the time is right. For now, you should be able to solve all the problems that I've posted below in the description. I strongly recommend that you solve all of them. You'll get the answer key for these in the next video. And for any questions, feel free to ask them in the comment section below.